So for this one, this is a classic problem. And we're going to use something that we've calculated before to solve it. And I recommend you get used to this approach. I call it the building block approach. You learn things that you've been shown before and apply them to problems to make them easier. So here's the deal with this one. We'll put in the values in a second. You got the X, Y, and Z axis here, but really this problem lends itself to cylindrical coordinates because you got two rings that bind this inner annular ring of charge density. So they have one at a radius of A and another one at a radius of B. And here's where the charge density is. It's in the XY plane. Regardless of what A and B are, it doesn't matter. That's rho S. Does everybody follow me as far as what the problem looks like? It's an annular ring. Think of it as a circle with a hole punched out. Now first they want the electric field, but before we do that, what we're going to do is get the voltage. Remember I told you the voltage is easy to get? Then once you get the voltage, you take the gradient of that with a minus sign and you get the electric field. Y'all with me? And we're going to do it on the z-axis. So now I remind you that last class we did this. We said if we have a loop of radius A and it's got a charge density rho L on it, and I wanted to know the voltage at any height Z on the axis. I'm assuming it's centered, and this Z-axis is something where the thing's centered about. It's in the XY plane. Then, if you remember, I told you could take all the charge on that ring, put it right here. Y'all remember that? I could take, if there's a charge density rho L, I could take all this charge and just call it Q, put it right here, and make as an assumption it's like a point charge to find the voltage here. How many remember that? All right, that's a real important point. So for this one, the voltage right here would be total charge around that loop would be what of radius A? Circumference of the loop, right? 2 pi A times the charge density, right? Times rho L, right? So take the total charge Q, which is going to be rho L times 2 pi A, and then divide it by, and what's the voltage from assuming the voltage at infinity is 0, what's the voltage from a point charge? Just Q over 4 pi epsilon R, correct class? And R would be this distance, right here. R would be the square root of Z squared plus A squared. So this means this is 4 pi epsilon naught over square root of Z squared plus A squared. Now that's what it would be if I had just a single ring, right? I'm trying to address your question in a way that should make sense, my logic right here. Y'all with me? Who asked this, Bob? Okay, does this make sense?
Yes, sir.
Now, make this fact. A professor used to say this all the time. Well, instead of having rho L, here, if it's got a surface, it would have a charge density of, or I could say the total charge would be rho S times 2 pi A, and then times d rho. Y'all follow me that that would have a thickness d rho in the horizontal plane? With me, guys? Everyone? All right. Now, if that's the case, then what I can do is say I can change A to rho. We'll just make it for any arbitrary rho. All right. This would become rho. And instead of rho L, we'd have rho S, and there would be a d rho here. Because d rho times rho S is an equivalent rho L. Y'all follow me? And it's still got the 2 pi rho. So that would be then the differential voltage right there for a differentially thick ring. I'm moving a little quick here, but y'all follow my logic on this one? How many do? Okay. Guys, over here, you okay with that? So now I'm going to get the total voltage here at a height Z. I'm going to find the voltage VZ by integrating the differential voltage. And I'm going to say V of Z on the axis would be equal to the integral. And here's my integration. Now I'm going to take something and now it's this little sliver thick. It's going to be at a radius rho, and the thickness of this is going to be d rho. and I'm gonna get the total charge on that. What I'm gonna get is the differential voltage from this ring here. And that means this R would be the square root of rho squared plus Z squared. And remember, I'm trying to show you that this is like it's just an arbitrary distance rho between A and B in the XY plane, and it's got a differential thickness, just like that. I'm trying to take and map that over here. Y'all with me? All right, so now I put the differential voltage from that differentially thick thing, which is going to be, let me do one thing here to make my life a little easier. You see how I have 2 pi and 4 pi? I'll make it 1/2, okay? Just to make my life easier. Now, over here, I'm going to have rho s times rho times d rho on top. I have 2 epsilon naught on the bottom plus rho squared plus z squared to the 1/2 power. And this would be from rho equals A to B. Now we know A is 2 centimeters and B is 6 centimeters, I guess, or whatever the limits were. And rho s is given from before as 5 nanocoulombs per meter squared, but we don't need to include that yet. Are you with me, everyone? Now we execute the integration. Now for this one, it's pretty straightforward, but you can take out the constants. Rho s is a constant, 2 epsilon naught is a constant, right? Then I'm going to do an integral. Well, the way I'm going to do this, I'll just let u squared equal rho squared plus z squared. Y'all follow me on this? This is simple substitution. Then I take a derivative. Now z is held constant here, so I get 2u du is equal to 2 rho d rho. And the differential with respect to z is 0 because z is held constant. Are you with me, everyone? On this, in terms of that integration, z is a constant height. So when I do this, the 2's go away, and I get u du is rho d rho, correct, class? And so I can have, this becomes u du, this is going to be unusual too. And this down here is just going to be u squared to the 1/2 power is just u. And it goes from u equals the square root of, take the positive solution of that, a squared plus z squared to u equals the square root of b squared plus z squared. Y'all follow me on this? It's a u substitution, right? Now, we can make an argument, or some people could, that, well, like, why, you know, if I take the square root of both sides, I get plus or minus the square root of rho squared plus z squared. Only the positive root makes any sense to take. And I could argue this, I can do it a different way if this bothers you. All right, so you come down here, what do you notice most about this integration? It makes it so nice. I got u over u, what is that? Yeah, what is the integral of du? U, right? Y'all follow me on this one? It's kind of a no-brain integration, but might trouble some of you. It looks too simple, I must have done something wrong. No, you didn't. So now this is equal to what? Rho s over 2 epsilon naught. And now when I put the limits in, I've got the square root of b squared plus z squared minus the square root of a squared plus z squared. You all agree with that? Y'all follow me on that? Looks a little odd, doesn't it? It looks like, hey, wait a second. That doesn't look right. Well, it's right, and here's how you check it. Let z go to infinity for starters. What's the potential supposed to be at infinity for a finite charge? 0, correct, class? Is it? Let z go to infinity. What do you see happening? I got 1 minus 1, don't I? As z goes to infinity, this whole term's going to infinity, square root of that. This is going to infinity, they kill each other off. Do y'all follow me? As z gets very large? Now, the interesting thing about that is that's the voltage on the z-axis for any A, B, and rho s. That's absolutely true. It's a little irritating, but you'll notice something about this. The largest voltage is when z equals 0. Then you have really B minus A, don't you? As the value here times rho s over 2 epsilon naught. Do y'all see that, class? Take a good look. Let Z equal 0. You would have B minus A, correct? B minus A's got some value. But then as Z increases, as you go up the axis, correct? Now what happens? These two terms get closer and closer, and in the limit as Z goes to infinity, it approaches 0. Y'all follow me on that? It's not the thing that, you know, you're used to seeing something like this, but get used to doing things that seem a little odd with integrations, right? They will. So now that's the voltage. How do I get the electric field? Do you all agree with me there? And I don't know how they did it in the book. I'm showing you the easy way, in my opinion. How do you get the voltage? If you got, and we'll put the values in a second. This problem's perfect. I looked at this earlier. Well, how do you get the electric field? Pardon me. The electric field in general is what? Minus the gradient of V. Y'all remember me doing this? Right. Minus the gradient of V. Now, that right there is a function of Z. We did it in cylindrical coordinates, right? We can take the gradient in either cylindrical or Cartesian, and here's something to observe. You'll notice that this is not a function of X or Y, but only Z. This is also not a function of phi or rho, right here. Do y'all see this? After the integration's done, it's only a function of Z. Is the only thing that can have a variation, right? Y'all with me? So now to get if you look at this in your back cover, I think it's or front cover one. I think it's in the back cover of your book, right? Yes. What is the gradient? What's the Cartesian? Well, this is on the z-axis. It would be minus dv dz az. Correct, class? All right, let's do it. And don't make this hard on yourself. Just look over there. Minus the derivative with respect to z of this. I think you all grant me I can take rho s over 2 epsilon naught out in front. Right? Matter of fact, I'm going to do that. And then here's the derivative with respect to z of the square root. Here, matter of fact, I'll write it instead of square root, I'll do it this way. I'll put b squared plus z squared to the 1/2 power minus a squared plus z squared to the 1/2 power. Now, what's that going to be? And it's in the az direction. Well, that's minus rho s over 2 epsilon naught, right? What's the derivative of this with respect to z? Can y'all read my writing? Yeah. I'm worried about that when I get these looks like, I don't know. I feel you know, you just can't read what I'm writing because my penmanship's slow. It's 1/2 b squared plus z squared to the minus 1/2. Isn't it, class? Y'all with me on that? Take a derivative, the 1/2 comes out in front. And then you get really this. Right? And then what else? Now you have to take the derivative of the inner part, right? And you get 2z. Isn't that right, class? And over here, it's going to be what? Same thing, minus 1/2. The 2z comes here, and you get a squared plus z squared to the 1/2 power. Y'all, and it's in the az direction. I'm just taking the derivative. There's nothing fancy about what I'm doing. Just take a derivative with respect to z. There's nothing, I promise you, it's trivial. Okay, now I'm going to do one other thing here, and this is, I'm in a habit of always doing this. You see I got 2 and 2. I'm going to cancel those. I always try to simplify things before I move along. So I got 2 on top, 2 on the bottom. I can do it a lot easier than you can. Thank you. Y'all with me? Now at this point, how do you want to proceed? I could pull the z out in front if you want, right? It doesn't matter at this point. You can. You can just say, I'll put, it's up to you though, minus rho s times z. I have a comment about why I'm doing that, by the way. Then I have 1 and 1 here, right? Isn't that right? Now, you know one thing about this. What should the electric field be right at the origin? Just your gut feel. What should it be? electric field? Zero, right? You can think about all the charge, the little differential electric field components from that charge are pointing at each other and canceling. There's nothing. Is it zero? If z equals zero? In fact, it is. That's the reason I brought z out in front, to make sure you see that. Y'all with me on that? Now they ask a value, specific value for a given value of A and B in row S, right? Now it's just plugging it in, and I'll do it here. So now they want the electric field, right, at the point z equals what? Help me. Anyone? 8 centimeters or meters?
8 meters.
8 meters. All right. So z equals 8 meters, right? We're going to get it in a second. What's A and B? I think it's 2 and 6, but I don't know if they're meters or centimeters.
Meters.
Okay. A is 2 meters, B is 6. Go ahead. And rho S we had down there, I erased it, was 5, was it?
5.
Is that coulombs per meter squared?
It's 5.
Nanocoulombs?
Nanocoulombs per meter squared.
Okay. All right. Therefore, if I go here, I have minus rho S. Actually, you know, it's gonna be a positive number because this term is larger than this term. It's got a minus sign in front of it. There's a minus sign here. Y'all see that? It will be a positive number. There's a minus here, and I know this is gonna be larger than this number. If I wanted to get rid of the minus sign, I could switch the positions of those two and get rid of it there, couldn't I? But anyway, I'll just write it. Got a calculator, check me on this, because I know they got an answer in the book. So I have rho S, or minus rho S. I'll put minus 5 times 10 to the minus 9. And then it's over 2 epsilon naught. Epsilon naught is about 8.854 times 10 to the minus 12. And then you're going to have 1 over, and here A is 2 and B is 6. So it's going to be, let's see, B squared 36 plus, and Z is 8, so it's plus 48 to the 1/2 power. Yeah, that's right. Minus 1 over, and then it's 2 squared, so it's 4 plus 48 to the 1/2 power. And if somebody can give me that and be in the AZ direction, I'd appreciate it. Just tell me what you get for this. Square root 84 minus 1 over square root 52.
8.35.
Volts per meter?
Yeah, sharp meeting.
Yeah.
Shoot, the 8 squared is 48.
Pardon me?
This 8 squared is
64, pardon me, you're right, my bad. 64, that was my bad. So that should be, yeah, you're right, my bad. Thank you.
About 6.
Would you, when you get the, for the whole thing, what do you get?
about 6.
6 volts? Is that right? 6 volts per meter AZ. What's the answer in the solutions?
It's 48 volts per meter.
It's 48 volts per meter?
That's what I got.
What'd you get?
I got
Well,
48.
from this equation?
Yeah.
Can you check this?
I also got 48.
From this equation? And what's the answer to book 48? All right, it's checking it then. Check it, I mean, this should be absolutely right, but it's the easier way to do it. I'm telling you that. Because if you do it with the differential electric field from each loop of charge and do that integral, it's a little nastier, I think. This is the easy way, in my opinion, to do it. I hope you understand and appreciate why you do it by calculating the voltage first, then doing the gradient. This is a good question you asked, by the way. I actually looked at this before. I got a couple of problems. That's a good one because it really showcases the benefit of using the voltage to get the voltage first, then get the electric field from the voltage. A lot of people don't think about that. You won't. A lot of things, you know, students will try to memorize formulas. All these formulas for different shapes. And the problem is with one change, if I change rho s to make it a function of position, all of a sudden all those formulas aren't worth a hill of beans. Then you have to go and get the differential voltage from a given sliver there, right? And rho s is a function of position rho. Then you would have to do the integration to get the total value of the voltage, when it'll change the answer. So I'm going to tell you, just memorizing formulas is not the wisest thing when it comes to something like this, because if rho s is a function of position, of radial distance, nothing I've done after that point applies, except to get the differential voltage here at a given radial distance rho. Then that would be 2 pi rho, the circumference times rho s, but rho s could be a function of rho. You all with me? And I do those things on purpose, because people that understand it will do well. People that don't, that just cram a lot and try to memorize stuff, really fall on their face. So I'm trying to give you a little clue on how I think and I make up quizzes and tests. All right. Okay, other questions? Did you all get it right now, whoever?
I'm still getting 6.
Yeah, I got 6 too, but I can't figure out what I'm doing wrong.
A Z or an 8 in the equation that you wrote down.
Oh, the Z up here?
Yeah.
I'm sorry.
That's why.
That should be a 8.
My bad.
That would make
I'm sorry. I'm trying to rush through this, and I apologize for that.
So it's just off by a factor of 8.
There is this Z I didn't put in. You're absolutely right.
Yep.
My bad. I am sorry. I guess I shouldn't have rushed that. Okay, other questions? That's a great problem. I got one for you. Same exact problem. Ready? Same exact problem with one twist. Matter of fact, you can do this in terms of just general A, B, inner radius, outer radius, and rho s. So I'm going to have something, well, rho s is going to change a little. So I'm going to have something, an inner loop, this would be the X, Y, and Z, of radius A, an outer part of the ring of radius B, and now I'm going to have a charge density here, where rho s is going to be equal to 1 over rho times some rho 0. All right. So the actual charge density is going to be a function of 1 over the radius rho. You all follow me on this, class? Now, how would you do that? This is a standard problem. You know, I'm really trying to help. Where do you always start? Remember, building block, right? Think voltage, then get gradient to get E field, right? All right. Well, if I come out a distance rho away, I got a thin loop here, right? And I'm not even going to bother with the thickness. I'm going to say this is out of distance rho, and I told you if you put all that charge at the distance rho, you could get the voltage at the height Z, right? Remember the differential voltage in this case. So that would be the total charge would be equal to 2 pi rho. That would be the circumference of that loop, right? Times the differential thickness d rho times the charge density that I made rho naught over rho. You all agree with that? That's the total charge. Then I would divide that total charge by 4 pi epsilon naught, and this would be z squared plus rho squared, right, to the 1/2 power. Now that would be the differential voltage from a ring of charge out here at a given distance rho of thickness d rho. Y'all with me? What's the one thing you see right off the bat?
Rows cancel.
See how the rows cancel? All of a sudden, this integration takes a different form, does it? Now you see the 2 pi and the 4 pi also gives me that 1/2, right? Are you with me? But this integration is what? That's a different integral, isn't it, class? That integration is going to result in, you would probably need is it trig? Let me see. It's going to be z over the square root of z squared plus, wait a second. It's going to be z squared plus rho squared to the 1. No, I'm sorry. It's going to be z over z squared plus rho squared to the 1/2 power. But I'm not worried about that. I will give you a table for this. But you see the fundamental integration changes. You all see this, class? And by the same token, I can do a lot of stuff like that, where you actually, if you understand the basics, I take this, that's the differential, then I have to integrate this from rho equals a to b to get the voltage, and then after I get that voltage, to take minus the gradient of that to get the E. The steps would be the same, but here's where it changes, because now the integration is different. Y'all follow me, class? So you gotta be sure you understand this from the point of view, regardless of what the charge density is, if it's circular or if it's symmetric in the XY plane, how you would go about getting the voltage to get the E. Okay. Other questions before I continue? Continue that problem. Why don't you do that problem? I'll give it to you for homework on OneNote, and then go ahead and do it. See, I want to see what kind of answers you get. I'll put down specifics for A and B, and for rho S. All right, for rho naught, I should say. That's a good problem. And there's so many like it out there. If you had physics, this is the kind of stuff physicists love to do from students, because they can take one problem and change a few things, and it changes the whole answer. Okay. Other problems? Other questions about voltage? Because voltage is so important, right? I gave you how many problems? 5 or 6? All right, did y'all do it? Any questions besides that one? That's a good problem. I'm asking that because we got a quiz coming up, and I want to make sure I answer any questions about voltage before you go to pick up. All right. So if there are no further questions, the next thing we talk about, and everything builds in this course, so now that we talked about the electric potential and voltage and the energy basically, and the work required for things to happen, the next section is on conductors and Ohm's law. Now, so this in the book is on page, it starts on page 176, but really 178 and 179 are the meat of it. And I want to tell you this much. When you did circuits, everything is what's called a lumped parameter or bulk elements. You have R. It was a jagged line. It could have meant a light bulb. It could have meant a resistance that's over a very long wire. It didn't matter about what caused it. You had a lumped R. You had a lumped L. You had a lumped C. In electromagnetics, when we talk about resistance, we derive resistance based on the geometries and the electrical parameters, okay? So in order to do that, I have to describe a new concept or do a new parameter that's used to define things that when they have a conductor. So if you have conductors, obviously you guys have been around for a while, you know copper's a good conductor. And you know that in general styrofoam isn't, right? That'd be an insulator. You know some basic things. So if we're talking about things that should conduct in general, and you have a geometric shape, there is a parameter called the current density, J. This is the current density. And J is equal to sigma, and sigma is called the conductivity. And the conductivity is in either 1 over ohms meters, or it's in the units of Siemens per meter. It doesn't matter, right? It's 1 over ohm meters is probably the one that's used more commonly. That's the units of that. And J is equal to sigma E is the electric field in volts per meter, and J as the unit of current density, or amps per meter squared. Just think of current density. Current is amps. Density means how much current flows through a given meter squared of that stuff. It's really the density though. Y'all follow me on that, class? Just like charge density. So this is the current density. And next, I make a few other claims. If you have a current density, if you integrate, and this is going to be just general for now, J dot ds over a surface area, now you get the current flowing through the surface, and that should make logical sense. These are generalities right now. I'll get to a specifics in a second. Y'all follow me on that? Also, we know that if you integrate E dot dl, a minus sign, and you don't have to have that minus sign, and I'll explain why in a second, and you go from A to B, that's equal to V BA, or it's a voltage difference between 2 points. Do y'all follow me in this class? Now, here's how we go about business if we're talking about calculating the resistance of any geometric shape. We have to do things where we assume stuff. So usually it's done this way. And I'm going to show you, first I'm going to show you the actual geometry of the thing, and then I'll describe the steps we go. So if you just have a rectangular block like this, all right, and the rectangular block has a length L, and it has an area A, cross-sectional area here, and it's got a conductivity sigma. Just imagine, dimensions are not important. You got a cross-sectional area, and it's along the axis L, and the cross-section is invariant with distance. That's another thing I should say. And then I run a current through there. So I have a battery, and I put a current I through there, and it's going right down this thing. I hope you can appreciate what I'm trying to show you. I'm saying the current flows right down the length of that rectangular bar. And then I make the assumption that current is going to be uniformly distributed over the area. Now I can add some dimensions. Some people always like coordinate systems, so I'll call that the z-axis. And if that current's going down the axis, the way I've done this is I assumed I. My next step is I'm going to get J. So J is equal to I over A, and it would be in the AZ direction. Remember, I didn't give you the value for A, I just said there's a given area, cross-sectional area, and it doesn't change over the length of that rectangular block. Do y'all follow me, class? So y'all agree that would be J. Whatever the units are, whatever the size, it doesn't matter. Now after I have J, I know that's equal to sigma E, right? Based on my statement, right? Sigma is a material parameter. So I can say that from here, I can get E is equal to J over sigma, or it's really I over sigma A, AZ. Y'all follow me on this? Now we're after resistance, and resistance is always positive for any kind of materials that can't store energy. You don't have to worry about anything I give you and have a negative resistance. There is a theoretical negative resistance possible. That would be that'd be a source of energy. Don't worry about that. So now I've got E, right? Once I get E, and here's the way I'm going, and this is the usual way you go. You go I, J, then you get E, and from E, you get V, and then once you have V, you get R is equal to V over I. You started with I, you got V, and the resistance should be, if you did it right, V over I. Does that make sense to everybody? The logic is tractable, right? Resistance is always voltage over current, isn't it, class? Always. So I have E, now I need the voltage. Well, the voltage is technically always going to be positive, so I do this in a very casual way. I just say it's the integral of E dot dl. I know it's going to be positive. In this case, E is equal to I over sigma A, AZ. I'm just showing you what's putting in here. I'm putting E as defined here. I'm going to integrate from this surface to this surface. What I want to do is find the voltage difference between that surface being the positive and that surface being the negative. I want that delta V. Y'all follow me? So here, I get this, and it would be dot DZAZ if I was formal, and we go over from 0 to L, over the length, and it's got to be a positive value. So here the AZ's cancel, and I get IL over sigma A, and that's the voltage difference. I'll just call it, I'll just leave that as V. Y'all follow me, everyone? Now once I have the voltage difference, I have the resistance, because that means the resistance of this is equal to V over I. There it is, V, so I have really IL over sigma A divided by I, and it would be this. Y'all follow me, class? And that would be the resistance of a bar between the ends of the bar if you had a constant cross section and you also had the cross section is invariant with length and sigma is a constant. Y'all follow me? Now you'll notice it's proportional to L. That should make perfect sense to you. The longer something is, the greater the resistance between the endpoints. And it's inversely proportional to the cross-sectional area. That should also make sense. The narrower something is, the higher the resistance. Correct, class? Y'all follow me? It should make logical sense. And you'll realize it's inversely proportional to the conductivity. So the higher the value of conductivity, the less resistance you would have for a given geometry. Does anybody know what the conductivity is of copper? I mean, the first one. Pure copper. All right, it's about 5.8 times 10 to the 7th, 1 over ohm meters, if you look in the back of the book. That's very high. Silver's a little better than that. Technically, a superconductor, if you ever read that term, has a conductivity that's tending to infinity, but that's not the real definition of a superconductor. Superconductor's fundamental definition is no magnetic field can penetrate into it. And currents are created to prevent that, and it gives it makes it looks like it has a conductivity that's in it. That's the fact, all right? But don't worry about that. I'm just telling you a few things you need to know. Now, that's for the simplest case. That's constant cross-section. You'll know the shape of the cross-section doesn't matter. This could be a wire, circular cross-section. It could be an elliptical shape. It could be a very thin area, right? As long as the cross-section is a constant, and the current density is uniformly spread over it, and that's an assumption, but it's generally speaking for DC currents, guaranteed to be true. That'll be the resistance. Now, the next shape I like doing, and there's several that that you have to be familiar with, is going to be spheres. Now, this is an interesting one. All right. So we're going to talk about two spherical shells. Then we'll talk about cylinders. I mean, cylinders where they're flowing from the inner to the outer radius, but these are sort of the standard things. So, when we're talking about a spherical shape, I'm going to assume I have an inner radius A, and then I'm going to have an outer radius B. And then bear with me. I'm going to dig a little tiny hole through there, and I'm going to take a wire, and I'm going to take it and put it to this surface, and assume this inner surface is metallized. And then I'm going to put a battery here. I'll just call it V. And I'm going to assume the outer surface of that sphere is metallized. So think of a hollow sphere. It's got aluminum coating on the inside. And then on the outside it's aluminum coated, but inside, between these halves, you have some material with a value sigma. So the current is flowing radially outward. Can you all imagine that? It's flowing from the inner conductor to the outer conductor. So J is going this way. And I'm just trying to show you the direction it flows. Now here's the thing. The amount of current that's flowing from the inner to the outer conductor is not a function of radial distance, but the current density is. Let me get to that. So if I come out a distance R, now I can say that there's a current density J flowing through there. This should make sense logically to you, right? It's flowing through a surface that gets larger the further away I go, right? It's a spherical surface, right? So I'm going to assume I, like I did before, now I get J. Well, J is the total current I, and it's divided by the surface area. Remember, I'm at a distance R. What's the surface area of a sphere, everyone? 4 pi R squared. You need to know that, right? Surface area, not volume. So it's 4 pi R squared in the AR direction. That means the radial direction. That should make sense. The currents, I is flowing, it's the same current through every spherical shell. I mean, imagine this, as you change R, the same amount of I has to flow through it. So once I get J, what's the next thing I get, class? E. And how do I get E? J over sigma, isn't that right? This isn't hard to see, right? So, I mean, sigma E is J, so if I have J to get E, I divide by sigma. That means it's equal to I over, and this is going to be 4 pi R squared sigma AR, right? Now I've got E. What's my next step? Voltage. How do I get voltage? Remember, I know it's going to be positive. Isn't that right? That's the reason I don't worry about that stupid thing. So I know the voltage is going to be equal to the integral of E dot dl, and that's equal to the integral of what? I over 4 pi R squared sigma AR, and then dl in this case would just be dr AR. There's two other components of that differential, but they don't have to be zero because you're dotting it with the AR vector into J, or into E, pardon. And here, R goes from A to B. Technically, there's a minus sign here. And I find out that this is equal to I over 4 pi sigma. And the integral of 1 over r squared is minus 1 over r, isn't it, class? Well, the minus sign makes it 1 over r, evaluated, actually, should do this, and it would be simply 1 over A minus 1 over B. That's the voltage. Trust me on this one, and I've got a hard deadline here because I've only got a few minutes. That's the reason I'm moving a little quick. Do y'all follow me on what I'm doing here? What's my last thing I'm doing? I wanted resistance. Class? V over I, and you'll notice that the I just gets erased here. So I can say R, between the inner and outer shell, it will always be positive. It's simply going to be equal to 1 over 4 pi sigma times 1 over A minus 1 over B. Now this is strict positive because A is smaller than B, so 1 over A is larger than 1 over B. Y'all with me? And that would be the resistance between two concentric spherical surfaces of constant value sigma. Here's a twist to this problem I like to give on quizzes. Hint. Let me say that again. This is a twist I like to give on quizzes. Hint. Sigma does not have to be a constant. Sigma can be a function of R, just like the charge density could be a function of radial distance. Y'all follow me on that? Now, if it is, where's the big change? Well, J doesn't change, does it? If sigma's not in there, right? I assume I, then I get J. Y'all with me on this? Where's the change? Right here. Suppose sigma was sigma naught R. Then this would be I over 4 pi R squared sigma naught, I over 4 pi R cubed sigma naught, right? Y'all follow me? And then the integration changes shapes from there. So just be aware, you have to know how to go through the steps methodically to get the answer. Don't memorize the answer. I've had this on, I cannot tell you how many times I warn people about, and come test time, they memorize these formulas and they just write them down. You're completely wrong here. How do we even give you anything for this? It's like, I told you not to do it, then you did it. What am I going to do? So what I'm trying to do is encourage you to make sure you understand the steps to the problem, okay? That's really what I'm trying. I'm not trying to frighten you. I'm trying to encourage you. And there's a fine line sometimes, and I'm not Bruce Person. Anyway, I just do my best. Y'all with me on this? Last thing I'm going to mention, is it over? It is. I didn't get to do several examples here, but when we get into capacitance, it's going to be the same methodology. We assume something, usually charged, then we get the E field, then we get the voltage, and then we know that, remember, capacitance is what? I mean, really, charge is voltage times C, right? So if we assume charge, get voltage, we take charge over voltage, and we get capacitance. It's the same method. I'll show you some tricks to that on Wednesday. We're going to have a short quiz on Wednesday on homework due today and this, okay? And I'll give you some more homework. All right, guys, go out and do good and stay dry.